PreCalc, PreCalc, PreCalc. This is your weekend edition. You could be looking at it after class on Friday the 19th or Saturday or Sunday or even Monday morning. We are studying our last topic for the year. It'll be three different days, and then we'll go back and review. So that means, or maybe we'll just do it in 2 days and go back and review. We'll see. The day is case 1 for graphing rational functions without a calculator, and the first case when the numerator's degree is less than the denominator's degree. This is review for you. What is a rational function? Well, you see the word ratio in the middle of the word, so that gives you a really big clue. So y equals 3 over x minus 2. A ratio is just a fraction. So when you have an algebraic expression with a numerator and a denominator, you have a ratio or a rational function. So you have learned to graph these in the past, so let me review how to do it. So we are going to notice that the degree of the numerator is the greatest power of x. So there's no value for x in the numerator, so we say it's degree 0. So the top here has degree 0. And the bottom here, the greatest power of x, this is 1. So we see the degree of the numerator is indeed less than the degree of the denominator. So it qualifies for our study tonight. So we are graphing again y equals 3 over x minus 2, and here's the procedure to use for all of them. You're going to find the horizontal, well, we'll start with the vertical. We're going to find the vertical asymptote, the horizontal asymptote, and we're going to find the zeros. Then we should be able to graph it fairly straightforwardly. So I call the va, ha, and a 0. So the the vertical asymptote is where the denominator is 0, because we cannot allow for a denominator to zero out. So for the va, you're going to look in the denominator, and that is what will cause that to zero out. X would be equal 2. So therefore, we will never allow x to equal 2, so we create an asymptote at that spot. It's graphed with a dotted line like that, and it is vertical. The graph will never touch or cross the vertical asymptote. It can get close to it, but it cannot touch or cross. Then we come to the horizontal asymptote. On case 1, where the degree of the top is less than the degree of the bottom, the horizontal asymptote is always the same. It is y equals 0, which is the x-axis. So you don't have to calculate anything. For case 1, it's always the same. Alright, so now we are graduating to the zeros. So what will cause this to be 0? We'll look for the x. The zeros are usually referring to the x-intercepts. Zeros means where's it crossing this axis? And where do we look here? For zeros, we are going to look in the numerator. And for vertical asymptotes, we looked in the denominator. Now we're going to fix our gaze on the numerator. And wherever that is 0 is where it crosses the x-axis. It is never 0 because it's a 3. So this has no x-intercepts. Does it have a y-intercept? So another way of thinking of this is sissy chart. 0 for x, what is y? 0 for y, what is x? So we just took care of when zeros where for x-intercepts is where y is 0. So we found there was none. But if we zero out x, we get y equals what? We get 3 over 0 minus 2, sorry, minus 3 halves. Alright, so I can graph that. 0 minus 1.5. Alright, so that's a 0. Alright, so it is another kind of 0. It's really those who we call these on the x-axis, we call those crossing point zeros. But there is also merit for talking about where it crosses the y-axis. So again, these were called zeros. Either they're both related to 0, but these are officially called zeros where it crosses the x-axis. This graph has none, and it has one intercept. So I'll call them zeros when they're on the x-axis sometimes, and I'll call them y-intercepts when it crosses the y-axis. Alright, so now we're ready to graph, but we need a starting point. So I'm going to put one more point on our sissy chart, and that will give me a starting point. I like to start over here and work this way. So backwards to how we read. So I'm going to say when x is large, like 10. So if I come way out here to 10, what will the y value be? And I don't have to be real exact about this, but I get 3 over 10 minus 2, or 3/8. So basically I need to recognize that is a small positive number. And that gives me a starting point. So this graph, when I get way down here, is going to be close to the x-axis because it is small. So it gives me a general starting point, and it's not going to cross this horizontal asymptote, and it's not going to cross the vertical one, so it's going to have to bend upward. So if I start here, I have no choice but to go upward. There's a rule about skipping asymptotes. Because I'm graphing this from right to left, I'm going to have to skip over into this section and see what it does. Well, it turns out if it's going up on one side of an asymptote, when you skip over it, it starts from down. So it's going to cross there, we know, and it's not going to cross here. So there's our graph of 3 over x minus 2. Alright, let's try a complication. The first complication is we're going to have more than one vertical asymptote. So we'll do one like this. Y equals x over x squared minus x minus 2. Alright, so we're going to do Baha, and we'll call them x and y intercepts. Alright, the vertical asymptote is what causes the denominator to zero out. Let's factor it to easily see what that is. So we get x minus 2, x plus 1. That equals that. So what causes this to zero out and this to zero out? Well, if this was to be 0, x would equal 2, and if this was to be 0, x would equal minus 1. So we found two vertical asymptotes, and they are x equals 2 and x equals minus 1. I'll go ahead and start my graph. So the complication is now we have more than one asymptote. We have x equals minus 1 and x equals 2. Alright, now the horizontal asymptote for this case is always y equals 0. Always, when the numerator is smaller than the denominator. Alright, let's see if we can find some zeros. That will be the x-intercepts. We always look and see what causes the numerator to be 0, and that will be when y is 0, x is 0, so it's going to cross here, and that is also a y, it's also a y-intercept, because the x and y axes meet at the origin there. So how can we tell? Well, when we were looking for where it crosses the x-axis, the zeros, you put a 0 in for y and solve for x. So this, in other words, what causes the numerator to be 0? So we got that one. So now let's zero out x and see what y would do. So if I put a 0 here, here, and here, do you see I also get 0? I do. So that's all I found for that. Now I just need a starting point. I like to go up to 10. So I get 10 over, looking at the factored form, I get 10 over 8 times 11. So 8 times 11 is like 10 over 88, which is a very small positive number. So again, I'm going to start a small positive spot, and as I approach the asymptote, I'm going to have to bend upward. Then I play, let's skip the asymptote, skip across, and we come, the rule says when you skip across, if you were going up, you start the opposite way from down, and it's going to have to cross at this 0 and go like this, skip the asymptote, come down and go like that. So do you see how we can sketch it without a calculator, knowing some principles? All right, complication, complication. There has been a complication reported. We're going to look at what happens when we have squared factors. I knew that you've been thinking about that. So, in other words, let's just take one like this one, 3 over x minus 2. We're going to take that bottom factor, x minus 2, and square it. So we're going to see what complication that leads to. 3 over x minus 2, just like the first one, except I'm squaring the bottom. Alright, so let's do Abaha x and y intercepts. Alright, what causes the denominator to be 0? X equals 2. Alright, I think that's exactly what we saw on the first example. I'll turn the paper over and check that in a minute. And then the horizontal one is always y equals 0, which is the x-axis. And now we're looking for x and y intercepts. So when x is 0, what is y? When y is 0, what is x? So when x is 0, we get y is 3 over negative 2 squared, which is 3 over 4, 3/4. So that was different. 0, 3/4. And when we put a 0 in for y, we ask ourselves what would make the numerator 0. And there's none. There's nothing that will do that. Alright, and the last thing is we need a large number for a starting point. So we go out to 10 and we get 3 over 10 minus 2, which is 8 squared, 3/64, which is tiny and small and positive. So we'll give ourselves a starting point. We bend up, and now I'm going to skip the asymptote rule because the squared factor here will not allow us to do that. Do you see how this quantity, no matter what number I put in here, if I put in negative 100, which is negative 100 minus 2, will give me negative 102. When I square it, I get a positive number. So this squaring of the factor in the numerator will not allow us to jump and go down here. So we're going to have to stay up and go like that. So squared factors cause volcanoes. That's not their real name. Alright, so squared factors in the in the denominator cause volcanoes. This volcano could be, if this was a negative out in front, that would change it to being a upside down volcano. So that might show up. Be watching for it. Alright, there has been a new complication reported. And that is our last complication of the day. Repeated factors in the num and denom. Has that been bothering you? All right, that's a complication. Let me show you what I mean. And that'll be our last case one. That's all the complications I can think of. So, what in the world do we mean by repeated factors in the numerator and the denominator? I don't see much repeated here. But once you factor it, you will. And while we're in the middle of this exciting lecture, let's go ahead and give the secret word that I won't even show on the screen this time. I'll just speak it. And the secret word is battery. All right, prove me you're listening well. And the secret word is battery. We factor the bottom and we get x plus 3, x plus 2. Now you see the repeated factors. Now, we already discussed that zeros are when the numerator equals 0. So this would mean there's a 0 at x equals minus 2. But down here, we've also stated that when we zero out the denominator, that's where we have a asymptote. So this is saying an asymptote at x equals minus 2. But it can't be a 0, which is a point, and an asymptote, because an asymptote forbids all points. So how can it be both? It can't. So let me show you what happens when we have a factor that appears in both positions. All right. Hold on to your socks. This is pretty interesting. When you have a factor in the numerator and an identical factor in the denominator, that will not cause an asymptote. No, no, no. It will not cause a 0. No, no, no. But it will cause something really strange. I'm going to put a little wavy line, and that's not what it causes, but that's to remind you when I'm graphing it to show you what it causes. So when I get to that spot in my graph, I think you will be quite shocked and amazed. Alright, so we're going to go as normal until we hit that little crack in our graph. We're going to do a Vaha x and y intercept. Alright, so we look in the denominator. We're going to avoid this repeated factor, but what else causes the denominator to be 0? Right here, x equals minus 3. X equals minus 3, so I'm going to put a vertical asymptote there. And what causes a horizontal asymptote? Always in case 1, where the numerator is less than the denominator, it's always the x-axis. And then we have that's called y equals 0. Then we have x and y intercepts. So if we zero out x, we get 0 plus 2, we get a 6 in the numerator. In the denominator, we get 0 squared plus 0 plus 6, so we get a 1. So we have 0, 1. So I'll graph that right there. And then if I zero out y, what would cause the numerator to be 0? X equals negative 2. But that puts me on the crack here, so I'm going to not call that a 0. So there's none. We'll see what happens when we get to this point of interest. All right, and then I want a large value to give me a starting point. So I'll use this factored form. 3 times 10 plus 2 is 3 times 12. So we get a 36, oops, that x goes over here. when x is 10. So, sorry, wrong side. So 12 times 3 is 36. And on the bottom, we get 13 times 12, which is what? 13 times 12. 13 times 12, 156. When you have 36 over 156, it's like 0.2, so it's a small positive number. You know, they won't always start here, but all the examples tonight have. So we're going to follow the rules, cross the 0 here, and this is not an asymptote, but something's going to happen there, and I'm not going to show you just yet. And then this will bend up, and then we'll play the game of asymptotes, jump over. But right here is not a 0, it's not a dot, it is not an asymptote, it is a hole. There's a hole in the bottom of the sea and on our graph. All right. So that's what happens. And you've seen holes before, so you're not totally shocked. One thing I did, and I'll show you how, I wanted to show you how this one up here related to the first one we did. So here we had no volcano, but this on the second one that was like it with the squared factor, it flipped up and became a volcano. And on this one we have a hole. And there's another point I wanted to shore up before we left, and that is here on this one, I forgot to mention when we graphed this, remember we were graphing from this starting point and we went up, we jumped the asymptote. Why did we cross the horizontal asymptote? Right here. We went right across as if it wasn't, and yet it's an asymptote because horizontal, and go back to this example and put this note near it. Horizontal asymptotes near the origin are not absolute. They're not very strong. You can cross them if you're in this area. If you're out here, you may not cross a horizontal asymptote. Vertical asymptotes are absolute. You never cross or touch them under any circumstances. So how did we know it went up instead of bending here and going down? And then that would cause this to flip up here because of the rule of jumping asymptotes. So that's a good question. The only way I know to answer it is right here to do some sissiness. So I should have brought that up when we did that. And that point, if we knew what happened at say x equals 1/2, we would know if it went up or if it went down. So we have to, so if it went all the way through, which is allowed, then we would jump the asymptote and do that. If it turns around and goes back down, then we would jump up and go like that. So which graph is correct? Let's put in 1/2 into this example, and we get 1/2 divided by 1/2 squared minus 1/2 minus 2. So let us see what that gives us. 1/2 over 1/4 minus 1/2 minus 2. So is that a positive value or a negative value? That is a negative value. I don't really need to know. Do you see how 1/2 is positive and this number down here is negative? So I was putting the 1/2 into this expression. I'm sorry, I was supposed to put in negative 1/2. Let me correct that. We're trying to test this at this point right here. Well, x is negative 1/2. All right, so this is negative 1/2. This is negative 1/2 quantity squared. This is a negative 1/2, and this is a minus 2. So now Let's see if it's positive or negative. We have a negative divided by a what? This is positive 1/4 plus 1/2 minus 2. So we have still a negative in the bottom. A negative divided by a negative is a positive. So we know at x equals negative 1/2 it went up. So we were correct, but sort of by chance because we didn't check. So here, this, and then we skip the asymptote, and this part here is, we were correct, but there was a part that we didn't check. So I thought of it at the end of the lesson, not when I should have. All right. So where was that other asymptote? At x equals -1. Let me put it back in. All right, so we were correct, but I wanted to give you that warning there. We weren't sure whether to go up or down at this point as we were tracing from right to left. All right, case 1. You will see these complications. Regular one, no complications. This one, where we have more than one vertical asymptote, and we're going to have to do some extra work to find out which way it goes. This one with repeated squared factors in the denominator, and this one where we have the same factor in the numerator as the denominator. All right, that's it for tonight, or this weekend, so we will see you bright and early on Monday, where we will tie up this discussion and get some practice on it. All right, that's it. Carry on. Miss you, Alex.